This is our Morse-Lee car with type 1, and this is square wave bursting. You can see my cursor here. So we have voltage, we have W, then we have I applied, and I have the apostrophe here to recognize that it's a V dot, right? It's a differential equation. And this is just epsilon times V naught minus V, the very simple example of square wave bursting. All the rest of this is the same. Then I just want to highlight this applied current. The applied current here, this is the general way we've written applied current throughout this course. Of course, I have it commented out right now because applied current is a state variable. But remember, you have I applied is IO, that's the bias, plus step, minus step, plus step, minus step. So you can bring it up, bring it down, bring it up, bring it down. You can bring it up as much as you want, down as much as you want, at times that you want. But if you leave these times, T0, T1, T2, T3, very high numbers, or you make the amplitude 0, then those steps never happen and you just have bias. In this particular model of square wave bursting, I'm not going to muck around with my equations on the left because we never do that. Once we have a model that's working, we stop playing here and we play here. The applied current is set to 0 at the time because I'm going to use the applied current as the slowly changing state variable. And if I set this in motion, I get nice bursting. On the left-hand side is voltage in red. On the right-hand side is I applied. And you'll notice that the I applied goes from about 34 up to about 41. Now, that should be ringing a bell. Remember, that brings you from your saddle node all the way through your show for square wave bursting. Everybody good with this model? Any questions about this model and getting this model to work? This is for you, so I'm happy to answer the questions as we need them. We're good? Okay. So I'll close this model now, and we'll start the more sophisticated physiological version. This is what I call Morse-Lee car type 1 square wave version 2. Equations are very similar, except now our state variable is now calcium. Again, we have epsilon, negative mu times I calcium minus calcium. There's our gating variable for Z. This one is a Hill function with n of 1, and kappa is 1. All that's written in your slides. So what does this look like when we run it? We have bursting. Voltage is on the left-hand side in the voltage regime we expect. And then on the right-hand side is calcium. And it's ranging between 0.6 up to about 2. And you should be able to glean from the trajectory that calcium increases during the burst and calcium decreases in the quiescent interval. So the dynamics of this one and the one before it, if you look in a time series, they look quite similar. Current, physiological current, outward current, increases during the burst and it deactivates during the quiescent interval. But in the simple square wave, applied current increases in the quiescent interval and applied current deactivates during the bursting interval. Yes?
Can you scroll up to your ODEs on the left there? Thank you.
Both square wave bursting. All right. If I make epsilon a smaller number, what do you predict? So I'll go from 0.005 to 0.002. What do you think will happen? EJ. Good job. all the phases slow down because the slow variable changes less quickly. Any questions about this model? I'm just going to move from one to the next, and then whatever you want me to do, I'll do that thing. But if we're good with this one, I'll move on. We're good? Marco? Yes? I faked it. I actually didn't hear what you said. 1 second. Yes, okay.
Would you be able to just scroll down to the bottom of it for a second?
Marco, do you have what you need? Yeah. Okay. I'm going to move on to elliptic bursting. So here's my polynomial model. So simple. I called it flagship because I was about your age and I was playing with the Fitzhugh-Nagumo model until I said I'm gonna futz around with this model until I can make it do type 3 bursting or elliptic bursting. And when I finally got it to work, I named it flagship because I was just so proud of myself and I never changed it. So that's the polynomial version. I think I have the, yeah, here's the elliptic version set up for Morsley-Carr. So this is Morsley-Carr with type 2 parameters. And if you look at my terminal window, which I think you can see, there's the equations. dV dt, dW dt, dcalcium dt. So this is the Morsley-Carr. It's a little bit more difficult to read than my equation window in Berkeley Madonna. But there's an equations window here as well. They're definitely not as pleasant to read. I think I'll just close it. Let's see if we can get the bursting to work. So I have this evolving, and I've added a different curve in red for calcium. And the black is the voltage trajectory. Okay, it just went off of the fold limit cycle bifurcation. And now it's zooming back into its steady state. And calcium is decreasing, so the calcium-dependent potassium current is turning off. And soon it'll start to destabilize as it passes through the Hopf point. Can you see how the oscillation is getting bigger? So it's growing now, and we're past the Hopf point, so back out to the stable spiking. So this is the Morsley-Carr version. This is not the simple polynomial version. So when this simulation finishes, I'll move on to parabolic bursting. It's about 3:05 right now. So I'll move on to parabolic, which is something you've never seen before. Yes, Abe?
What's this model once again?
I'm sorry, what?
What's the name of the model?
This is elliptic. The reason why people call it elliptic bursting is because they think that this looks elliptical, this diagram. I don't really like that, but I don't have a better one. Square wave makes sense. Parabolic makes sense. Elliptic to me, eh. Okay, so back to the simulation. Do you want to see anything else here, or should I move to parabolic? Aiden.
Can you go back to the Morse car?
This one?
Sorry, not Morse car, the Berkeley, the action one. I don't know why I said Morse car.
So this one you could get directly from the lecture notes. This is not hard to program. This one's easy.
I just want to check my syntax.
Gotcha. Okay, shall I go to parabolic? Hearing no objections? All right. Parabolic. This one is the most challenging model we've dealt with. I'll make the font bigger in a moment. This is by far the hardest one to code and the hardest one to, debug. But that's fitting for us, moving towards the pinnacle of the class, pinnacle models of the class. Increase text size. Here we go. Okay, so looking at the top here, we have G calcium, M infinity, V minus V calcium. This is the Morse-Car spiking calcium current. This is the one you've dealt with many times. G leak, this is the leakage current. This is our delayed rectifier type current. This is our KCA with the gating variable Z. And now here's G calcium S with the gating variable S. Lam W is just the same thing as phi. It's just another name for phi. Okay, don't worry about that. It's just the same thing as phi. And now my calcium equation, negative mu, then this is G calcium times M infinity. That's the spiking calcium. G calcium S times S. And then both of those gating functions are multiplied times the driving force. So, gentlemen in mid, I'm looking right at you. I'm forgetting your name, but you asked me, how do you program this in? So the way I did it, and you could do it numerous different ways, is I just put in parentheses my two gating functions, G calcium times M infinity, pertaining to that one right there, G calcium S times S, pertaining to that one there, and then I multiplied them with parentheses times the driving force, creating two calcium currents contributing to the increase in intracellular calcium. So that's how I did it. Okay, unpacking the rest of this. There isn't any steps here, no step amp. I just use I/O for bias. Because parabolic bursting is sophisticated enough, I'm not going to perturb it. It's not bistable. So there's no point in me giving it steps. Remember with our fast square wave, we played around with tri-stability, bistability. We're not going to do that because it's a SNCC. It's never bistable. Okay, so I'm going to shrink the equation window so that we can watch the system evolve. And there we have, is this 16 seconds or 16,000 seconds? 16 seconds. And you know this because in Morse-Car, voltage is always in millivolts, time is always in milliseconds, currents are always in microamps per centimeter squared, conductances are always millisiemens per centimeter squared, and our thetas and s's are always in millivolts. And what is capacitance? Microfarads per centimeter squared. So if you look at one of these bursts, really, really close up, let's look at this one. How many spikes do we have? I have 39. Anyone get something else? 39 spikes per burst? So if you go home and run this model and you don't get 39 spikes per burst, either I'm wrong or you're wrong. And if it's reasonable, like if it's, oh, I got 34 or I got 42, it's not wrong. It's probably just, there's probably a parameter that's incorrectly typed or a parenthesis in the wrong place. As you know, of your experience, if your model is really wrong, it don't work at all. But if your model is really close to right, it gives you an answer that's slightly different than your neighbor, and you guys got to figure out where's the disparity. So 39 spikes per burst. It is 10 after 3. We have 9 more minutes together. What can I do? What do you want to see? Scroll down. So again, all of these equations are written properly in the lecture notes on the slides. Sanjoli. You would like me to show? Yes. Yes. Sanjoli would like to see the slow phase plane. So to do that, I will go to Graph, choose Variables, and I don't need V anymore. I need S and Z. So I'll put Z on the x-axis, and I'll put S on the y-axis. And I will let the axes be automatically adjusted. So you can see that the Z criticals are going to go from the lower left to the upper right. So given what you know about the physiology of this system, if you were presented with this diagram, and forget you have this tail right here. Let's say you didn't see that part right there. You just see this closed orbit. And I asked you on a test question, where does the burst begin and where does the burst end? How would you work that out? I've done this many times. How would you work that out? Because you can't really tell by looking at the diagram here. That actually looks like the spikes are slower, but you don't really have explicit time in the phase plane, so you can't really rely on that to tell you. But knowing about the physiology of the system, you could figure this out. Anybody have any ideas here? This is Z, and that's S. Where does the burst begin? Where does the burst end? First of all, we already know the answer. It begins here, and it ends there. But if you didn't know that, if you were just given this picture, do you think you could use your intuition to figure it out? Is there anything you could think about here? Like I've said a couple times, you know the physiology of the system. You know what S is. You know what Z is. Well, one way to think about it would be like, okay, I know when Z and S are both low, both of the currents are off. The calcium current is off, and the calcium-dependent potassium current is off. And when Z and S are high, both of the currents are on. So that intuition alone should tell you that, well, at the beginning of a burst, I would expect those currents to be lower. Because at the beginning of the burst, calcium should be low. So you wouldn't expect S to be high yet, and you wouldn't expect Z to be high because calcium is low. In the quiescent state, calcium should be low. Physiologically, there's no current, there's no spiking, no calcium currents. Calcium should be low. And at the end of a burst, we know that the calcium-dependent potassium current should be high. So at least we can be certain that Z should be low at the beginning of a burst, and it should be high at the end of a burst. You can be a little bit less sure of S. But your intuition should be able to help you work out where a burst should begin, where a burst should end. Does that make sense? Physiologically? You know what the gating variables do. All right. I think we have maybe another minute. 3:15. We have another 4 minutes. What can I do? Yes, sir.
Should we follow the values for the parameters on the left side or the ones you change for the right side?
Always interact with your model here. What you see here is what this is doing. What you see here is the same unless there's an asterisk. If there's an asterisk, I've changed it. So Berkeley Madonna tells you everything you need to know. Whatever you see happening in the left window, if it has an asterisk, I've changed it from what I programmed it. And whatever's in this box right now is what's happening here.
Could you show the parabolic function on
I'm having a hard time hearing you.
Oh, could you show the parabolic function on plane?
Sure. P-plane? You mean in the phase plane?
No, isn't there something you said we could put in P-plane?
Oh,
Yeah.
yes. Okay. Okay. All right, let's do it. You're going to have to read the equations to me, though. I don't... no, I'll find them. I'll find them here. Okay. So here are the equations. Going to P-plane. So x, y minus 4 times x times x times x minus z minus 4 times x minus 1 minus y. Z is just a parameter. Let's make it just 0.1 for the moment. Let's go back to this window for a moment and just watch the system evolve. This is the wrong one. I want to get a good value for z. So it looks like if I leave z somewhere like negative 0.5, it'll be quiescent or oscillatory. Yeah, that'll work, 0.5. So go back to P-plane, make it negative 0.5. Get the null lines. Okay. Now you notice here, you have a cubic null line, and the intersection point is right on the right-hand knee. So we should be at that unique bistability point where you could have a stable, steady state, or an oscillation. So we'll throw down some equilibrium, not equilibrium, we'll throw down some initial conditions. Make this 2, make this minus 2, graph it again. Nah, that should be minus 4. That's much better. So I'll throw down some initial conditions, but I want to make sure I'm going in forward time. Went to the oscillation. And I'll ask it for the stability of that equilibrium point. It's uncomfortable calling this a stable equilibrium point. It's calling it an unstable equilibrium point. This is saying it's an unstable equilibrium point. If I go back to my Berkeley Madonna, you know what? It looks like there may not be a stable equilibrium point at negative 0.5. If I make it negative 0.6 and I graph the phase plane, I just want to show you a stable equilibrium point. There it is. Okay, we found it. So I was making a very bad mistake. Z is like the gating variable for calcium and potassium current. As Z gets bigger, the hyperpolarizing current, and then the system gets more stable. So far so good? Okay. So it's about time for class to end. We've just run out of time. I'll see you Thursday, and I'll bring a tripod.